can make it more reasonable to do this. So here's your sine curve. And again, we go through this a lot. This is pi over 2. Some of you labeled wrong. You put pi, then pi over 2. And here's your 1 to your negative 1. Your sine curve follows this pattern. It keeps on going. And again, down here as well. Now, your reciprocal says take whatever values they are, take the reciprocal of that fraction. The 1 over 1 is going to give us a 1. Negative 1 over 1 is going to give us a negative 1. We're okay with these guys. What we can't do is take the reciprocal of 0 over 1, because that becomes 1 over 0. Wherever your graph hits your x-axis at those zeros, this is where your asymptote is. Now, even if you can't remember it, just draw it. You should be able to see it. Your graph is not continuous. It goes like this. It breaks up because of your asymptotes. Now, your domain. Follow your domain. A lot of you were able to give me this graph because these are the nicer ones, the two that go off the curves, but you couldn't give me the domain. Now watch. You can't use a 0. You can't use a 1 pi. You can't use a 2 pi. What else do you think you can't use? 3 pi, 4 pi. You see the pattern? N pi. N pi, where n is any integer. Now, watch. You have to set your domain up to say real except x equals n pi, where n is any integer. And your range is exactly the opposite of your sine and your cosine. Where that goes from negative 1 to 1, this goes from negative infinity to negative 1. Oops. And from 1 to infinity. Now, again, just think this out with me for a minute. If I change this, and this was my, if I change this, and I now want y equals cosecant 2x, do I want more curves in 2 pi or less curves in 2 pi? What's my frequency say? What's my frequency? 2. What was my other frequency? 1. Think in terms of sine if you need to. This is going to tell me 2 says change my frequency. I want more curves in 2 pi. So if I have more curves in 2 pi and I'm doubling them, I have to half the space, don't I? Do you see it with the sine, right? If I have 2 curves in 360, I have 1 curve in 180 every pi. I halved the time to do it. So your asymptotes are going to half the time. If you think about it, think with me out loud. It works. Here's my sine curve. I would have to take my sine curve and I would have to make a complete one in here. I would have to go from here to here to here to here and back down to here. Now, my cosecant would have to go off of these guys. So I have to cut this in half, cut this in half. Do you see it? I would have to have double the curves, half the time. So my asymptote would also cut in half. My asymptote would come to pi over 2. This is where I would be crossing over here. This is where I would be crossing at the pi over 2. I'm going to do half the time. Yes? No? Okay. All right. Cosine. This works the same way. This works off your cosine curve. Your cosine curve just starts up here. It works the exact opposite, just like your tangent and your cotangent do. Because the zeros and the ones go every 90 degrees. If you do your unit circle, the 0 and the 1s go every 90. Now, again, here's my asymptote. So write these out. This is at pi over 2. What's this one at? 3 pi over 2. So I've got a 1 pi over 2. I've got a 3 pi over 2. What comes next? 5 pi over 2. Therefore, n pi over 2 when n is an odd integer. You can find these yourself. The range is the exact same. And again, they come off the corners here, the edges. Okay, so your domain is going to have to say real except x equals n pi over 2, where n is an odd integer. And your range would be the same as your sine and your cosecant curve. Good? Good, Anthony?
Yeah.
Good. So Anthony, talk to me about your tangent curve. How do I attempt to graph your tangent curve?
Find your asymptotes first.
So where would your asymptotes be on your tangent curve? Don't turn around and ask your friends.
I'm not.
No phoning a friend. No phoning a friend. Up here. Where's your asymptotes? So at pi over 2, because we can't take a 90-degree tangent, think off of this guy. Up here, watch. If it's up here, isn't your 0 in the same position down there? Exactly across from it? Exactly across. So if this one won't work 1 over 0, this one's not going to work negative 1 over 0. And at 3 pi, the easiest one to catch is your 45-degree angle. It's a 1 in quadrant 1. It's a negative 1 in quadrant 4. So it constantly goes like this, all the way across. And you notice, Anthony said you couldn't use 1 pi over 4, 1 pi over 2, 3 pi over 2, 5 pi over 2. This is the same as your secant. And what's your range for this tangent curve? All real numbers. Your range is all real numbers. An amplitude change will not affect your range. It's all real numbers. Okay? Now, your cotangent curve works the opposite. It has to. Because while they're on these quadrants, your cotangent says x over y. I can do x over y. I can do that part here. What I can't do now are these guys. At the 1, 0, this is going to give me an undefined. So they work exactly the opposite, just like your sine and your cosine do, because it's a shift of every 90 degrees. Now your cotangent says your asymptotes are going to be here, at the 0, at the pi, at the 2 pi, at the 3 pi. See it? Your curve to your 45. There's your 45. It's got to go this way. That's the easiest way to figure out which way your curves go. Once you get your asymptotes, do a 45-degree angle. It can't go the other way. These go like this. And so therefore, your domain for your cotangent says all real except x equals n pi, where n is any integer. And again, this has the same range as your tangent. Okay? Any questions on those? This is important that you get these. You don't even have to memorize them. If you're going to memorize something, at least memorize that the two c's work the same, and the tangent and the secant work the same. This way, if you can get the secant and the cosecant, you can get the cotangent, you can get the tangent from there. And the secant and the cosecant should be the easiest, because that works off of your normal curves. I know everybody struggles with the tangent. It's a different looking function. It's not continuous. It has its own asymptotes. It has its own barriers. And if you just draw your unit circle, it will make more sense. Well, the tangent is opposite here. The cotangent is opposite there. It makes sense because that's the position of that 0. So draw these out. Make them make sense. Some of you panic because it's trig and you say, oh, I don't know how to graph this. But make it make sense. Now let's hit your review. Your first one, if you take a look at it, you might want to write it out a little differently. 1/2 sine 1/2 x. There's your frequency, there's your amplitude. So the first 1/2 just changed your amplitude. It took, there's a negative, sorry. It took a range from 1 to -1, and it went from -1/2 to positive 1/2. That's all it did. The negative just reflected this. Instead of, and it's easier if you do this. Watch. Take your normal sine curve and multiply it by -1/2. I'm multiplied out here, right? Isn't that multiplying by sine? So multiply this guy. God bless you. This is your pattern that you're going to go. At the 0, at the -1/2, at the 0, at the positive 1/2, at the 0. Now you just have to figure out where your frequency is. Your frequency says half the curve in 2 pi. So how long is it going to take me to complete the other half? Another 2 pi, which puts me to where? 4 pi. I don't even need to do the formula. I can figure this out by looking at this. It's logical. So here's my 2 pi. I'm going to do half my curve. Here's my 4 pi. There's my other half. That's all that there was to this. This one, all that's different is this. It's the same exact piece, but it says a vertical shift of 3. We're going to take this and put this over here. So you took this guy, which had a, what did this 1/2 do? What kind of transformation is the first 1/2? A vertical shrink. Instead of coming up here, I shrunk it. This 1/2 does a horizontal stretch. It's the opposite of the way we think, because usually the 1/2 does a shrink, but this 1/2 stretches this period out. And then this 1/2 does a vertical shift of 3. You have a reflection in your x-axis as well. Now, we did this to figure out your highs and your low points. We also started, watch, here's your range. This is your original sine curve. Our amplitude went to 1/2, so multiply this by 1/2. Now, the last thing we did was shift this up 3. We added 3 to everything, not multiplied. So add 3 to this, add 3 to this. 2.5 to 3.5. Oops. If you convert this to an improper fraction, which would look better, 5/2 to 7/2. There's your range. Easiest way to do it, rather than try to figure it out on your graph. Find a pattern and keep the pattern all the way through. Questions? I know you're thinking you can't wait till trig is over, but hang in there. This is not so bad. Okay, your cosine curve. Your cosine is the opposite. At the 1, at the 0, at the -1, the 0, the 1. My negative gives me a reflection in the x-axis. My 3 gives me a vertical stretch. Multiply these guys by -3. That gives you this pattern. -3, 0, 3, 0, -3. That's the pattern I'm going to follow. Now, this is a frequency change. It tells me I want 4 cycles in 2 pi. I want 4 cycles every 90 degrees. And I just did one 90 degrees over here. And I did another 90 degrees over here. So every 90 degrees, I'm getting 1 cycle. And if you do it out here, here's your 2 pi over here. Each one of these has to get 4 pieces in here. And you're going to go follow your pattern to do this. It's going to look like this all the way through. It's got to give me 4 of those. 4 in 360. Say it that way. It makes a lot more sense. This one, if you put in your calculator 4 in 360, every 90 degrees, you need to set your table to every quadrant, which is 90 divided by 4, which is 22.5. So if you don't understand how to set your quadrants up, your calculator is not going to show you on your table. So we've got a shrink. It shrunk the period. It's like an accordion. Did everybody find these equations? Let's do the first one. Find your resting point. From the highest to the lowest is 8, divided in half is 4. There's your amplitude, 4. Come up 4 or down 4, whichever is easier to do. Make your resting point. Here's your transformation here. Okay, I went, and this is tricky, and this is what your Regents likes to do too. I went to 4 pi. 2 pi is right here. So how many did we fit in 2 pi? How many complete curves of the cosine went in 2 pi? 1. Good. So your frequency is 1. We had a vertical shift up 4. We had a reflection in the x-axis. So you put your reflection out there, your amplitude changed, frequency of 1, and we shifted it. I won't give you any phase shifts in your transformations because you would never be able to know if it was a cosine or a sine. Okay. And this guy over here, move this over. Okay, let's take a shift down. So go from high to low first. Your 2 units. So each one is 1. So your amplitude is 1. From here to here, measure your x-axis. From here to here, you went down 3. You took a reflection. There's your 1, -1. And I went to 2 pi again. So 1 frequency in 2 pi. For some odd reason, the cosine curve is always a little bit more difficult to find than the sine curve. I think everybody's always likes the one that starts at the 0 and looks like a nice pretty picture. It looks like it actually got the wave going on here. The cosine is the opposite way. It starts at the top and goes down. Everybody tends to like a sine curve better. Okay. Let's see if we can move on. Did I give you this part? Oh, you had not 11? Okay. This one? 12? Now, if it's helpful, pull this fraction out. Pull the fraction out. This is your amplitude. This is your frequency. Your amplitude goes to 5. So which changes? Your range or your domain? Range. Good. So instead of going from -1 to 1, from -5 to 5. Agree? Okay. Your frequency changed. Your frequency says you're going to do, now listen carefully, you're going to do 2/5 of your curve in 2 pi. 2/5 of it. It's almost like a half of your curve in 2 pi. So did you shrink the period or did you stretch the period? You shrunk it. No, you stretched it because you're stretching him out. 2/5 of that curve in 2 pi. Normally, don't you do a whole curve in 2 pi? It's got an opposite effect with the fraction. Because if you do half of your sine curve, what do you do to your sine curve? You stretch it out, right? So if you do 2/5 of your curve, you stretch this curve out. It's going to take you more than 2 pi to do 1 period, isn't it? Because you only can do 2/5 of it. It's real close to a half. Think of like what happens with a half. So we say 2 pi over b. There's your period. 2 pi over 2/5. We keep. We change. We flip. And out comes this. It's going to take you 5 pi to make 1 complete cycle. If I did it with a half, doesn't it take me 4 pi to make a complete cycle? So it's slightly less than 1/2. 2.5 would be 2.5 over 5 would be exactly a half. So you've got a stretch, a horizontal stretch, just like you do when you do sine of 1/2, and you've got a vertical stretch because of your amplitude change. I didn't ask you to graph it. 5 pi, if I asked you to graph to 5 pi, if I just went by pi's, you'd have to make 4 equal quadrants in here. 4 equal quadrants. If you thought about it in degrees, just if you took 5 pi divided by 4, 5 over 4 pi, it's a little bit more than a pi each time. So if you went like this, and a little bit here, and a little bit here, you'd get your 4 cycles. It's only a sketch. So I wouldn't be looking at exact angles, I would just be looking at a sketch. Don't let the fact that that's 2/5 and not a half. Work it the same way you do a half. Did I give you 13? 14? Okay. 14 is a phase shift. This t is the same as x. It just said g at t instead of g at x. That's all it said. So it's the same as your x. Amplitude change. Is that a stretch or a shrink? It's a stretch. It's a fraction, but it's an improper fraction. So isn't the top larger? Right? So I have a stretch here. This is my vertical stretch. Even though it's a fraction, don't let it fool you. It's greater than 1. This guy is a phase shift. So now, instead of my sine curve going like this, there's my 90. Which way am I shifting this? To the right. It works the same as your quadratics do. And instead of starting here, I'm going to start at pi. So I need to expand this 2 more pieces, right? And then I need to go 0, 1, 0, -1, 0. I just shifted it over pi units. Okay? My radians. So from here to here is my shift. My cycle says take this, use x if you need to, set it equal to 0, set it equal to 2 pi. Normally I go from 0 to 2 pi. I am now going from pi, add this over, to 4 pi. Let's see if that makes sense. Oops, wait, let me see. 3 pi.
T minus pi the whole b.
T minus pi is not your b. Your b is still 1. B is in front of the t. It's a horizontal shift. That would be like your c in there. They consider this shift your c, the negative pi. And the vertical outside, that one is considered a d. I didn't give you anything else but besides your frequency of 1 whenever I did a shift. I want you to be able to see the shift where I got c over b. Because if I change your frequency and shift it at the same time, it's a little harder. So map it out if you can't see it. Move it over here. Yeah, that's 2 pi. That's 3 pi. From pi to 3 pi gives me a complete cycle. Okay. This one, you should be able to do this. Everybody do this one? I want 2 sine curves in 2 pi. Therefore, every 180, I block it off, and I make 4 quadrants. Follow your pattern.
That's number 18.
You don't have this?
That's
number 18. Number 18? Okay, check number 18. Sorry. I had a different answer key that didn't match the sheet, but it has the same problems on it, so I'm trying to mix and match. Thank you. So 2 frequency, amplitude 3. We've got an amplitude, a vertical stretch, and what does the frequency of 2 give us? A horizontal shrink. I need 2 of them, so didn't my period now go to pi instead of 2 pi? So I shrunk the period. Horizontally, I'm shrinking the period. And these increments, this just says like where your quadrants go. Every 45 degrees, I hit one of your cycles. Your 0, your 1, your -1, your 0. You should be able to graph this. How many more do we have? One more? Okay. Now, if you put this in your calculator and you don't change your table and you go every 90 degrees, you're only going to see what you see at the 90s. And those are just all zeros. So you've got to be able to change your table to match where your quadrants go. Your change of table in your calculator has to be your period divided by 4. It has to span your quadrants. Otherwise, 90 is not going to work. A zoom trick on this, you'll graph it, but you won't see it in your table. Maybe, seeing the graph might be a little bit easier for you to look at, but try to follow the pattern and go through it with the pattern. Is this your last one? Yes? Okay. Here's another phase shift. I'm shifting it pi over 2, which is how many degrees? 90. I'm shifting it 90 degrees. Which direction? To the left. So now, instead of going from 0 to 2 pi, I'm going from -pi over 2 and pi over 2 short of 2 pi. 3 pi over 2. Doesn't that make sense? I shifted it to the left. Just so look at me. 0 to 2 pi. I'm here. To the left. -pi over 2 to 3 pi over 2. See your period now? Without even having to worry about adding them and subtracting them. Set it equal to 0, set it equal to 2 pi. Do the actual shift. Pick up the curve and shift it over. Amplitude 3. Regular cosine curve and shift it over. Start here. Follow your pattern. 1, 0, -1, 0, 1. See it go to 3 pi? Okay. Monday's a test, guys.